Hi, everyone. Thank you for watching my talk. My name is Ioana Bercea, and I'm currently a postdoc at the IT University of Copenhagen, also part of Basic Algorithms Research Group in Copenhagen. This is joint work with Guy Evan from Tel-Aviv University. Our paper is on the topic of data structures, more specifically perfect hashing, in which we are given as input a set S of size n coming from a universe U of size U, and we'd like to maintain a perfect hash function pi, which assigns elements of the universe indices in the range n plus r, such that elements of the input set receive unique indices. These indices are also known as the hash codes of the elements, and n plus r is known as the hash code range. A data structure for perfect hashing answers hash code queries such that given a query element x, it returns the correct hash code of x if x is in the set, and it is allowed to return an arbitrary value otherwise. We are interested in the dynamic setting, in which additionally, the perfect hashing data structure supports insertions and deletions to the set. And in this context, an important property that we care about is stability of hash codes, which requires that the hash code of an element does not change as long as the element is continuously in the set. Another further distinction that is relevant in the dynamic setting is that between extendable and non-extendable data structures, and it has to do with a type of information we assume about the input set. In the non-extendable setting, n denotes an upper bound on the cardinality of the set at all points in time and is known in advance. Therefore, space can be pre-allocated and the hash code range does not change throughout the lifetime of the data structure. In the extendable case, in which we're interested in this paper, nt indexed by time denotes the cardinality of the set at time t. And we require that the space of the data structure be expressed as a function of nt, in particular that it is dynamically allocated, and the hash code range changes also as a function of nt. The performance guarantees that we care about fall into major categories. With respect to space, we'd like our data structure to be compact in the sense that it uses a number of bits that is within a constant of the lower bound. And with respect to time, we want to execute all operations in constant time in the worst case. This is in the word RAM model, in which each memory access reads or writes a word of W contiguous bits, and standard computation on words can be performed in constant time. We'd like these guarantees to hold with high probability in the sense in which we will have some notion of bad event, either related to space or to time. And we want to ensure that the probability of such bad events is polynomially small in the size of the set, and that this holds for a polynomial number of insertions and deletions. Now, perfect hashing is considered a fundamental data structure, usually used in the context of other data structures. Perhaps the oldest such application is in the context of dictionaries. A dictionary is a data structure that answers membership queries of the form, is the element X in the set or not? And a simple solution using perfect hashing allocates an array T of length, the hash code range of the function, and upon insertion, stores an element X at the index indicated by its hash code. Because the perfect hashing is injective, there are no collisions in the hash table. And furthermore, membership queries can be executed in constant time by checking if at the position pi of X in the array, we find the original element that generated it. This was one of the oldest approaches to get dictionaries with constant time membership queries, out of which you might remember the celebrated result of Fredman, Komolosh, and Semeradi in the static case. I will mention here that in this context, stability means that once an element is inserted into the hash table, it never moves around the hash table. Now, there are other applications where perfect hashing is used. Two of the main ones are related to the membership problem. One of them is retrieval, in which we receive as input key value pairs and answer questions of the form, what is the value of X? The guarantee in retrieval is that if X is in the set, then we retrieve the correct value of X, and otherwise we're allowed to retrieve an arbitrary value. Now, a simple solution for retrieval using perfect hashing is the same as before, as in the hash table design, but here, instead of storing X, we store its value at the index indicated by its hash code. Yet another relevant problem is that of filters. These are approximate dictionaries in the sense in which they answer membership queries with a one-sided error. So if this queried set is in the input set, then the filter must always answer yes, and otherwise it is allowed to make a mistake with probability at most epsilon. And several works have noticed the connection between filters and retrieval in the sense in which you can get a filter by storing a specific value alongside the element in the retrieval, and that is the output of a pairwise independent random hash function with range 1 over epsilon. There are other problems where perfect hashing shows up, and it tends to simplify their designs. And furthermore, this idea of assigning unique stable IDs to elements is something that several other applications are interested in. As such, perfect hashing has a long history in the field, primarily focused on obtaining static data structures in which that don't allow insertions or deletions, and for which the set is known in advance. In the extendable dynamic case, the only work that we are aware of is by Ditzfilbinger, Carlin, Melhorn, Meyerhoff, De Heide, Ronert, and Tarjan. This is a dynamic version of the Fredman-Komolor-Semeredi dictionary. Its hash code range is quite big. It is a constant factor within a constant factor of NT. And crucially, their data structure requires rebuilding, which crucially uses the fact that it has access to the elements of the set. And as such, the hash codes that they obtain are not stable, and updates take amortized constant only. Perhaps the closest work to ours in the dynamic setting is non-extendable. This appears in a series of papers by Mortensen, Pei, and Petrashku in STOC 05, and Demain, Meyerhoff, De Heide, Pei, and Petrashku in Latin 06. And they consider the problem of designing stable hash codes in the dynamic setting. They obtain data structures that perform all operations in worst case constant time, and they give a matching lower bound for this problem. Unfortunately, they notice the non-extendable nature of their problem, and they emphasize that n represents not the current size of the set, but a fixed upper bound on the size of S. Similarly for R, which influences the hash code range. And they further note that this assumption seems necessary because the hash codes must be stable, and the hash code space is fixed and defined in terms of n and R. Now, this seems to suggest that there is an inherent tension between extendability and stability. And indeed, at first sight, it seems that they might be incompatible. So the first hint in that direction is that deletions may force stable hash codes to be out of range. For instance, consider the scenario in which we've inserted n elements and we want a hash code range of the form n times 1 plus 1 over log squared u. Now consider inserting n over log u more insertions. The hash code range in the extendable setting grows accordingly, and some of these newly inserted elements will for certain be allocated hash codes within this newly allocated hash code range. Now imagine deleting n over log u elements, but this time deleting the earliest inserted elements. They are guaranteed that the hash codes assigned to them are within the original n1 plus 1 over log squared u hash code range. And so if we maintain that the hash codes be stable, we will have elements for which at this point in time, their hash code would be out of range. The second challenge that seems to suggest extendability is a challenge is that a perfect hashing data structure does not store the elements of the input set. So consider the classic construction for getting extendable data structures, which is what we will use, of employing a non-extendable data structure, a fixed capacity data structure that is used as long as the size of the set is between some 2 to the I minus 1 and 2 to the I. As soon as the size of the set grows, we employ another instantiation of the data structure with double the capacity, and we use that as long as the size of the set is between n and 2n. Now, in order for this construction to work, we essentially have to pretend that this active instantiation of the data structure contains all the previous elements that were inserted in the previous instantiation. And in essence, it's as if all the insertions that were made in this instantiation have also been made in this new instantiation. And here is already, you can see the problem, which is that we cannot move elements around because we do not store the element itself. So having said that this task is challenging, we nevertheless asked ourselves what kind of stability, if any, can be achieved in the extendable setting. And the good news is that quite a lot can. So we showed the first perfect hashing data structure that is simultaneously extendable and has stable hash codes. It is extendable in the sense in which it has constant time worst case operations. The space is proportional to the size of the set, and furthermore, it is within a constant factor of the lower bound, even from the non-extendable setting, and it works for arbitrarily small ranges of the form NT over polylog U. It is stable in the sense in which if we only have insertions in our data structure, then the hash codes are guaranteed to be stable. And if we allow arbitrary deletions, then it is almost stable in the sense in which at most a constant number of hash codes have to change per operation. Now, the way we obtain this construction is by first proposing a simple architecture that consists of 3 elements. The first component, which we call the hash code repository, is responsible for maintaining the set of free hash codes in the range and supports 2 operations. The check-in operation, given an element X, assigns X a free hash code, marks that hash code as taken, and returns some value associated with X that may or may not be the same thing as the hash code. The checkout operation receives a free hash code and frees it if it is taken. The second component is a retrieval data structure that is responsible for storing the value associated with X. And finally, we have a decode function, which, given X and the value associated with it, can compute the true hash code of the element if the element is in the set, and otherwise it is allowed to compute an arbitrary value. To see a simple instantiation of this architecture, consider a hash code repository, which is just a linked list of the free hash codes, and returns a value that is exactly the hash code assigned to the element in the range. Now, the corresponding decode function associated with this is just a trivial function that returns the value associated with X, which, if X is in the set, corresponds to its true hash code. The problem with this simple approach is that for the ranges that we consider, it takes too much space. In particular, the value retrieved by the hash code repository is log n bits, which means that the retrieval data structure has to store log n bits, which for our ranges is too much, in the sense in which the lower bound suggests that the whole data structure should instead spend on average all of log n bits per element. Now, in order to fix this situation, we employ a very classic technique, which is balls into bins, and we implement the hash code repository as a collection of m smaller hash code repositories, which we call motels. Each of these motels corresponds to a distinct interval of the hash code range, and each of these sub-ranges have fixed length C. Upon a check-in operation, the element X is randomly hashed into one of these motels and receives an index in the corresponding interval, which we refer to as the room of the element. The value returned by the check-in function is exactly the room that X receives in the interval, but crucially, not the index of the motel. The corresponding decode function with this strategy takes the room of X and then shifts it appropriately by the length of the range, multiplying it by the index of the motel corresponding to X. The technical aspect here is in setting B and C to ensure that there's always room for elements that hash into a motel, and that the total hash code range of these motels is within the desired bounds. It turns out that the right setting of parameters sets C to poly of n over R, which for the ranges that we consider is equal to polylog n, which means in particular that we can implement each motel to execute all operations in constant time worst case, and such that the whole hash code repository requires a linear number of bits. And furthermore, the value that the retrieval data structure stores, which is the room of the element, takes log C bits, which is exactly theta log n bits per element. And this implementation, in fact, recovers the original design of Mortensen, Payne, Petrashku, and Demain et al. And in fact, our architecture can be seen as a reinterpretation of their design, with, of course, the added benefit that it can be made extendable. Now, to see how this might be achieved, we will first focus on making the hashcode repository extendable. And note here that the intention behind our design is to ensure that the value that the retrieval data structure stores never changes throughout the lifetime of the data structure, which means that the burden of stability falls solely on the hashcode repository and its associated decode function. Now, as I've mentioned before, we employ the classic technique of doubling and halving. For the purposes of this talk, we will assume for simplicity that we do have access to the elements, so we can move them around, and we're only processing insertion, so we're only going to do doubling. And we consider a division of time into phases, where phase I corresponds to the time in which the cardinality of the set is between 2 to the I and 2 to the I plus 1, which is equal to some parameter n that we set. As we move from one phase to the next, the number of motels in our hashcode repository doubles. We allocate new motels of the same capacity as before. In order to hash elements in this new phase I plus 1, we employ a global hash function, which means that we read one more bit off of it in order to determine which motel we go into. And here we note that if an element stays in the same motel, so hashes to the same motel index as before, we say that it stays in the legacy motel. And if it moves into a new motel, if it reads a value of 1 of the global hash function, then we say that it moves into a fresh motel. Crucially for our purposes, the room that the element is assigned into a motel doesn't have to change. So you could move to a new fresh motel, but you would keep your room number. Now, in order to make sure that the hashcode range does not double all of a sudden, we further consider a split. We further split a phase into theta n over r generations. And in each generation, we gently increase the hashcode range. And we do so in an asymmetric manner in the sense in which the legacy motels keep their original hash codes, keep their original capacity, and only the fresh motels keep growing in range. As they grow in range, we transfer the elements from the old motels into the new motels, keeping their room numbers. So one can ask in this new extendable strategy, how does the old decode function that I described behave? In this particular case, the decode function would be some function of whether you're in a legacy motel or in a fresh motel. What is the current generation? Meaning, have you already been moved into your fresh motel or have you not? And obviously the specific room inside the motel that you're assigned. And in particular, one can notice that the source of instability in this case comes from elements that now move into a fresh motel. Elements that stay in the same motel according to the original decode function never have to change their hash codes. It is just the elements that move into the fresh motel. So the difficulty in our paper is in keeping track of when these events happen and being able to revert them for the purposes of stability. Now, in order to achieve this, we introduce the concept of ghosts, which can be best explained through a binary tree that keeps track of the occupancy of a room throughout the phases. So imagine that you have an element X residing in some room in motel alpha during phase K. In phase K plus 1, this room essentially duplicates. There's a room now in the legacy motel and a similar room in the fresh motel. And imagine that the element X in phase K plus 1 now moves into the same room in the fresh motel. When this happens, we say that X leaves a ghost in the room in the legacy motel. Every time X moves, it leaves such a ghost in the corresponding legacy motels. And furthermore, a ghost is passed down generations until a new element comes into the same room. Now, what does this have to do with hash codes? Well, notice that according to the previous decode function that we looked at, all the rooms in these motels have their own unique hash code associated with them that is easy to compute. And furthermore, these rooms that keep staying in the legacy motels all have the same hash code associated with them. What we would like to ensure is that once X is inserted into a room, it keeps the same hash code, as if it never checked out of this room. So we would like to pretend that X stays in the same room and keeps hashing into the legacy motel, regardless of where X actually is. The way we ensure this is that if a new element checks in at insertion time into a room that has a ghost, it cannot take the hash code associated with this room because X owns it now, and instead takes the hash code that is associated with the room in which X moved into. So this room in the fresh motel also has a hash code. It is a different hash code from the room in the legacy motel, but it is unoccupied because even though the room is taken by X, the hash code that the decode function gives it is not taken. X already has a hash code. X, in fact, has the hash code associated with this room in the legacy motel. So when Y moves in, it takes the hash code of X, and this can be easily tracked by seeing in which phase X moved, and then computing the appropriate motel index, and then applying the simple decode function that we previously looked at. Now, in order to ensure that this process works, we have to check for two main things. One is that there are no collisions. So Y does not take the hash code of a room that has already been assigned to something else. That is ensured by X. So X is in that room. Nobody else can take this hash code but Y. And furthermore, that there's no overflow. So no hash code is assigned twice. And that is ensured by the fact that Y switches hash codes with the most recent element that gave the room a ghost. The technical difficulty in our paper is in showing that we can ensure this while ensuring constant time operations in the worst case, and while only spending log U over NT bits per element. This is to keep track of the history of these ghosts. And furthermore, that the value that we end up storing in the retrieval data structure is also not very big. To give you an idea of the kind of information we store the room of X naturally, its insertion and the phase and generation at insertion time, and the switch phase of the room if there was any ghost in that room. We showed that all of this takes theta log NT over R plus log U over NT bits per element, which is in accordance to the lower bound. And furthermore, we have to ensure that given all of this information, the decode function can compute the correct hash code of pi in constant time in the worst case. Now, the last step left in our construction is to see how to get an extendable retrieval data structure. This is best understood in a larger context that includes the applications of perfect hashing that I've mentioned at the beginning of the talk. As we've seen, there are several reductions between these problems. In the particular context of retrieval, there was no known dynamic construction that did not use perfect hashing. So in order to get around this, we propose a new reduction that employs a filter to obtain a retrieval data structure. This is based on a technique introduced in Bercea, who used it to obtain a dynamic filter. We use it to obtain the first retrieval data structure that is extendable, uses 1 plus little o of 1 times NT times K plus theta NT log U bits to store K bits of satellite data per element, executes all operations in worst case constant time, and as a bonus, also performs approximate membership with epsilon equal to 1 over polylog U. What this means is that if the queried element is in the set, the retrieval data structure will return the correct value associated with it. And if the element is not in the set, then it will tell you so with probability at least 1 minus epsilon. Now, our work can also be seen in this larger context. In particular, we show how to get a perfect hashing data structure out of a retrieval data structure. That is through the use of the hash code repository. And if you follow all of these reductions to the maximum, you get as a corollary of our work that any compact, even a non-extendable dictionary that uses some constant times the information theoretic lower bound can be used to obtain a succinct extendable dictionary whose space on top of the lower bound is only theta of n log U bits. The intuition here being that the constant in the compact dictionary, the constant in front of the lower bound, is essentially transferred to this low order term. Thank you very much. and I look forward to your questions.